Black holes as universe generators. Could every black hole in our universe be creating new universes? This idea sounds like science fiction, but it forms the basis of a serious scientific theory proposed by physicist Lee Smolin, called cosmological natural selection. This theory suggests our universe might be just one in a long lineage of universes, each born from a black hole in a parent universe. Black holes represent extreme environments where space-time becomes so curved that nothing, not even light, can escape. At their center lies a singularity, a point where our current understanding of physics breaks down completely. The laws of general relativity stop working, and quantum effects become important in ways we don't yet fully understand. This breakdown of physical theories makes black holes perfect candidates for extraordinary phenomena. In the early 1990s, Lee Smolin proposed a radical idea. The matter that collapses into a black hole might bounce and create a new universe on the other side of the singularity. According to Smolin's theory, every black hole in our universe could be the birth site of a new universe, like seeds dispersing from a cosmic fruit. These new universes would expand into their own space-time, completely separate from our universe. We would have no way to observe or communicate with these baby universes, just as they would have no way to detect their parent universe. Each would appear from the inside, to begin with something like a Big Bang. Cosmological natural selection proposes that each new universe would have slightly different physical laws than its parent universe. The fundamental constants that govern physics, things like the strength of gravity, the mass of the electron, or the strength of the nuclear forces, would be slightly altered in the baby universe. This variation introduces a cosmic evolution similar to biological evolution. Universes that produce many black holes would create many offspring universes. Those offspring would inherit characteristics similar to their parent universe, but with small, random variations. Some variations might increase the number of black holes the new universe produces, while others might decrease it. Over many generations, this process would favor universes with physical laws that maximize black hole production. Just as natural selection on Earth favors organisms that reproduce successfully, cosmic natural selection would favor universes that make lots of black holes. The mathematics involves complex principles similar to biological evolution. Random mutations occur, and those that improve reproductive success spread through the population over time. The population consists of universes, and the mutations are changes in the fundamental constants of physics. If cosmological natural selection is correct, our universe should have physical laws optimized for black hole production. When physicists examine our universe's fundamental constants, they do seem well suited for creating black holes. For example, if gravity were slightly stronger, stars would collapse more easily into black holes but might not last long enough to produce heavy elements needed for planets and life. If gravity were slightly weaker, stars might never collapse into black holes at all. Our universe seems to be in a sweet spot for significant black hole production. The conditions that favor black hole production also seem favorable for life formation. Stars need to burn for billions of years to produce the heavy elements needed for planets and living organisms. These same long-lived stars eventually collapse into black holes. The complexity needed for life appears connected to the conditions that produce black holes. This connection suggests a possible explanation for why our universe appears fine-tuned for life, rather than requiring a designer who calibrated the fundamental constants to allow for life. Smolin's theory suggests that universes evolve toward conditions that favor black hole production, which happen to also favor life's emergence. Smolin's theory provides a mechanism for universe creation that doesn't require an initial beginning to everything. Our universe could be the descendant of another universe's black hole, part of a cosmic lineage stretching back indefinitely. Each universe in this chain would have slightly different physical laws from its parent. One strength of this theory is its testable predictions. For instance, it predicts that neutron stars should have a maximum mass of approximately twice our sun's mass. Observations of neutron stars have been consistent with this prediction. though more data is needed for confirmation. The theory has faced criticism from other physicists. Leonard Susskind has argued that it relies on older black hole concepts that may not be correct given recent developments in black hole physics and string theory. The information transfer mechanism from parent to baby universe might not work as Smolin's theory requires. Despite criticisms, cosmological natural selection remains an intriguing explanation for our universe's properties. It addresses fine-tuning without requiring infinite random variations or a designer who set the constants perfectly. If correct, our universe is part of a vast cosmic evolutionary tree, with each black hole representing a branch point where a new universe begins. Black holes would be generative sources of new universes rather than simply destructive objects. Each would mark not an end but a beginning, a cosmic reproductive event giving birth to a new universe with its own space, time, and potentially its own form of life. String theory and parallel branes. What if other universes exist right alongside ours, separated by dimensions we can't perceive? This might sound like science fiction, but it's actually a serious possibility proposed by one of the most advanced frameworks in theoretical physics, string theory. While the previous theories we've explored suggest other universes might exist far beyond our cosmic horizon or in different bubble universes, string theory offers the possibility that other universes might be incredibly close to us, separated only by dimensions our senses can't detect. String theory represents a fundamental rethinking of what makes up our universe. Instead of viewing particles as tiny points with no dimensions, string theory proposes that the fundamental building blocks of reality are incredibly small, vibrating strings of energy. These strings are unimaginably tiny, much smaller than atoms, smaller even than protons or electrons. The way these strings vibrate determines what kind of particle they appear to be, similar to how different vibrations on a guitar string produce different musical notes. This elegant approach helps solve one of the biggest challenges in physics, unifying gravity with quantum mechanics. For the mathematics to work properly, string theory requires extra dimensions beyond the 3 spatial dimensions and 1 time dimension we experience daily. In our world, we move freely in 3 spatial dimensions up or down, left, right, and / backward plus time. String theory suggests there are additional spatial dimensions that we don't perceive, typically 6 or 7 more depending on the specific version. These extra dimensions are curled up or compactified to an incredibly small size, perhaps at the Planck scale, approximately 10 to the power of -35 meters. Imagine an ant walking along a garden hose. From the ant's perspective, it can move forward and backward, but the circular dimension around the hose is so small that the ant doesn't perceive it as a dimension for movement. In some versions of string theory, our entire universe exists on a 3-dimensional membrane, or brane, floating within a higher dimensional space called the bulk. Think of our universe like a single page in a pop-up book. The page itself has length and width, and the pop-up structures represent our 3-dimensional space. But this page exists within the broader context of the book, which has additional dimensions the characters on the page can't access or perceive. Other branes could exist parallel to ours within this higher dimensional bulk space. Each of these branes could host its own universe, complete with galaxies, stars, planets, and potentially life forms. These separate universes might operate according to different physical laws, with different fundamental constants than our universe. The separation between these universes is fascinating. According to string theory, most of the fundamental forces, electromagnetic, strong nuclear, and weak nuclear forces, are confined to the branes themselves. This means light, electricity, magnetism, and the forces holding atoms together can't travel between branes. This explains why we can't see or detect these. Other universes directly light from their stars and galaxies can't reach us because it's trapped on their brane. However, gravity is special. In brane cosmology, gravity can leak into the extra dimensions, traveling through the bulk space between branes. While we couldn't see another universe on a parallel brane, we might potentially feel its gravitational effects. This property could explain why gravity appears so much weaker than the other fundamental forces. Some of its strength may be leaking into the extra dimensions. These parallel universes could be separated from ours by distances measured in extra dimensions that might be incredibly small, perhaps just millimeters or less. But since these distances exist in dimensions we can't perceive or travel in, these universes remain invisible and unreachable to us. Scientists have developed experimental approaches to search for evidence of extra dimensions and parallel branes. If gravity can indeed travel between branes, we might detect subtle variations in gravitational strength at very small distances. The Large Hadron Collider has been used to search for evidence of particles or energy disappearing from our brane into extra dimensions during high-energy collisions. So far, these experiments haven't found definitive evidence, but the search continues as technology improves. The scales involved are so small that detecting these phenomena remains extremely challenging. If string theory's explanation for parallel universes on branes is correct, it transforms how we think about the boundaries of our universe. The edge isn't some distant place billions of light years away. It's a dimensional limitation. We're confined to our brane not because of spatial distance, but because our particles and forces, except gravity, can't leave it. There could be another Earth on a parallel brane with its own version of our solar system, galaxy, and perhaps even versions of us. But unlike the identical copies we discussed in infinite space theory, these parallel versions would likely be quite different, existing in universes with potentially different physical laws. String theory continues to evolve as physicists refine the mathematics and search for ways to test its predictions. Whether parallel brane universes actually exist remains an open question. But the possibility that other universes might be incredibly close to us, just separated by dimensions we can't perceive, represents one of the most fascinating frontiers in our quest to understand what might exist beyond our cosmic horizon. Testing the untestable. If these other universes exist beyond what we can see, how could we ever know they're real? This question strikes at the heart of a fundamental challenge in modern cosmology. The scientific method that has served us so well for centuries relies on observation, testing, and verification. But what happens when the very nature of your theories places their subject matter beyond direct observation? Testing theories about what might exist beyond our observable universe presents unique challenges. We can't simply build a bigger telescope or send a probe to observe these hypothetical other universes. They're either too far away, separated by dimensions we can't access, or fundamentally disconnected from our universe. Yet despite these obstacles, scientists have developed clever approaches to search for indirect evidence. Scientists focus on finding observable consequences within our universe that would only make sense if multiverse theories were correct. Consider how astronomers discovered Neptune not by seeing it directly at first, but by observing unexplained perturbations in Uranus's orbit that could only be caused by another planet's gravitational pull. The key is identifying unique signatures that conventional physics cannot explain. One promising approach examines the cosmic microwave background radiation, CMB, for patterns indicating collisions with other bubble universes. If our universe is one bubble in a multiverse, our bubble might have collided with another in its early history. Such a collision would leave distinctive circular regions with different temperature profiles in the CMB. Scientists search for these collision signatures using data from satellites like WMAP and Planck. So far, results remain inconclusive. Some teams claim to find possible evidence of bubble collisions, while others argue these patterns could be explained by random fluctuations or instrumental effects. The search continues as data analysis techniques improve. Another approach involves searching for inconsistencies in physical constants that might suggest interaction with parallel branes. According to string theory, our universe exists on a three-dimensional brane floating in higher dimensional space. If other branes exist nearby, they might influence our universe. This influence could manifest through variations in fundamental constants of nature. The fine structure constant, which determines electromagnetic interaction strength, should remain constant throughout our universe. However, if our brane interacts with another, this constant might show tiny variations across space or time.